like with exponential functions, with logarithmic functions, we have lots of applications in the real world. So this is why you're studying them in applied math. One very common example to tell students is the pH scale. pH scale, when you say a certain substance has an acidity of 5, that 5 comes from the way we calculate logarithms. Okay, so once you, I don't know how many of you are in chemistry, some of you are, right? None of you are in chemistry this time? Okay. Well, if you are going to get to take chemistry and you're going to get to calculate the pH of a certain solution or substance, you will see the logarithms in that calculation. Okay. So first, I'm going to introduce to you what is the logarithm of a number. The logarithm of a number, log of a number in a certain base k, is the exponent to which we have to raise a certain base to, so we can get that value n. So if I have to think about this in a way that I understand right now, because I've seen that format before, I would think about it as a power, okay? So to what, this is the base, to what exponent do I have to raise this power to so I can get the number n, okay? And this is the x, and that's the value of the logarithm. So if I just ask you that, what is the logarithm in base k of n, right? The question is, k to what number gives me n, okay? An example is this one. 2 to what number is equal to 8, written as a logarithm, would be written as logarithm in base 2 of 8 equals that number that I just asked you for. So 2 to what exponent is 8? Everybody says 3, right? And that's how you calculate a logarithm without the calculator, right? You just think about the exponent to which you have to raise the base to so you can get the value that's inside the logarithm. Okay, so now the number 2, when you write the logarithm, the base of the logarithm is always written a little bit below the word or the shortcut word log. Log comes from logarithm, okay? And then the input of that logarithm, the number 8, is written at the same level with log, okay? And then equal and 3 also the same level. So log 8 equal 3, same line, 2 is a subscript. Make sense? Okay. There are a few conditions for the logarithms to exist. So the base k has to be a positive number and cannot be 1. These two conditions are the same as the conditions we used for exponential functions, okay? And then the n also has to be, we call it a non-negative number, so it has to be bigger than 0 strictly. You cannot input in a logarithm something less or 0, okay? It will give you an error, okay? Now your calculator has two buttons for the calculation of logarithms. You have log and you have ln. Both of these are special base logarithms. So a log would be a logarithm base 10, and an ln is the natural logarithms. That's a base e logarithm. E is called the Euler's number. It's a special irrational number, has a value of approximately 2.7, and letter E comes from Euler, a famous mathematician, okay? It's called sometimes Euler's number, okay? So both of these are very special logarithms that have lots of applications, again, in the natural world, and that's how your calculator is programmed, and you can only directly calculate logarithms in these bases. You don't have, if you take pre-calculus, then you learn how to deal with other base logarithms. We'll come back to those notations later on. Actually, do I come back to it? Let me see. So we'll write it down and we insist a little bit more later on. But before we get there, this is new for me. I haven't had these pages in the previous year, but I always felt like we need to do a little bit more more of an introduction to logs, just so you understand where they come from. So for that reason, I've added some of the intro examples that I actually use for my pre-calculus classes as well. So let's just practice switching from one notation to another, from logarithmic notation to exponential notation, and vice versa, because they are related to one another. All of the numbers that we use for exponents are participating in the numbers that we use for logarithms, because in the exponents, you calculate the value of that power. In logarithms, you calculate for that exponent. So the way you look for the numbers is different, okay? So log in base 3 of 27 equals 3. In the exponential notation would be the same base, which is 3. And then I just like to do this arrow, comes around, pushes the 3 up into the exponent like that. And it will equal the number 27. And once you write it down in the exponential form, you can see that it's true. 3 to the exponent of 3 is 3 times 3 times 3, which equals 27. Okay. So your logarithm calculates for this 3 here. For the 3 in the exponents, the question is always 3 to what exponent equals 27? Log of 100 equals 2. Now, log notation, when you don't see a base, it's just notation for a logarithm in base 10. Okay, that's a special kind of notation. So we can rewrite it as log in base 10 of 100 equals 2, just so you can see that base. All logarithms have bases. They don't exist without them. And then again, we take the 10, it's the base, and we push the 2 into the exponent. So 10 to the 2 equals the 100 underneath the logarithm. And that's the exponential notation of this logarithmic notation. So 10 squared equals 100. It's true, right? So then, in case you're wondering if you're right or not, you always look at your equality. Does that make sense? Did I write something that's true? If you did, then it's correct. Again, the logarithm always asks the question about this exponent, and that's the answers to logarithms. Backwards now. So you have an exponent, write it as logarithms, okay? So 2 to the exponent of 4 equals 16. So you always have to write the word shortcut log. The base is the same. So it's going to have a base 2, just like the exponential form. Now the answer is the input, so 16. And then again, we're solving for the exponent, so the exponent is on the outside, 4. So basically, the input and the output get, like, they just switch positions. A 1,000 equals 10 to the 3. I'm still gonna rewrite it as 10 to the 3 equals 1,000, just so you can see the same as the previous example. Log, always base 10 as a first step, so you don't forget that all logarithms have bases, of 1,000, so the input is the answer, and equals always the exponent. And then one more step, because we don't write any logs in base 10 with a base in there, so we just get rid of the base. Log 1,000 equal 3, because that's still the same thing as the previous one, okay? It's just notation for a logarithm in base 10. Is it clear? There you go, pre-calculus, everyone. Not that hard, is it? Okay, So now let's see if we can find out without using a calculator the value of some logarithm. So I'll give you a really straightforward method that I'm going to use for a really simple example that you can guess without the method. But then the method will apply for more complex examples too, and then you'll be able to figure it out without, again, the calculator. So the first thing that I would do when I have to find the value of a logarithm, so it's asked me evaluate log in base 2 of 16. I say, okay, question mark, but instead of question mark, because we're in grade 12, we put X. We don't know what it is, make it equal to a value as a letter, right? X or A, doesn't matter what the letter is. Then the second step is write it in exponential form. So you just take 2, push the X into the exponent, 2 to the X equal 16. So you're basically defining the logarithm. To what exponent does the base 2 have to be raised at, or to, so you can get the answer 16, right? And then either you know the answer directly, or now you can just rewrite 16 as a base 2, so you can see that exponent. 2 to the X equals 2 to the 4, that's 16 as a base 2 exponent. Now you can see directly that X equals 2, 4. Make sense? So that means my logarithm in base 2 of 16 is 4, because I was looking for that exponent. Is it clear? Any questions? Okay, log in base 9 of 3 equals X. Then we say 9 to the X equals 3 to the 1. Now the 3 to the 1, I can't really change anymore, so I can have the same base, but the 9, I can rewrite as 3 squared. So you write 3 squared X equals 3 to the 1. And the 2x now has to equal 1 because the bases are the same. So the only difference now comes from the exponent, but they must be equal because we created an equality. So then 2x equals 1. Divide both sides by 2. X equals 1/2. So the value of this logarithm, log in base 9 of 3, is 1/2. Make sense? This would be harder to think of, right? If you say, okay, to what exponent do I have to raise 9 to so I can get 3? You have to take square root of 9, right? And the square rooting of a number is the exponent of a half, you know? But that's a bit more like advanced, or way back to grade 9. I don't know if you remember grade 9, but this is grade 9 stuff, all the exponents, okay? So log in base 2 over quarter equals X. We do then 2 to the X equals a quarter. Now we have to write both as a base 2 power. The only one that needs to be rewritten is the 1/4. So first, we can just rewrite 1/4 as the reciprocal notation with a negative in the exponent. And because we have done a lot of questions in our minutes, you see negative exponents, right? So we just do 4 to the negative 1. So we got rid of the fraction format of that reciprocal notation. Then 2 to the X equals, now I focus on the 4. How do we write 4 as a base 2 power? 2 squared, but it's going to be negative because I had the negative 1 from before. So negative 1 times 2, so negative 2. Now directly you can see that the X is, or must be, negative 2. So log in base 2 of a quarter equals negative 2. Again, a little harder to think of without actually writing the work on paper. when you ask, okay, 2 to what exponent is 1/4, you know? You have to think, you have to jump through a few hoops to get there, right? So it's easier to do that kind of mental math on paper. And the last one is 2 logarithms combined. So log in base 2 of another log in base 3 of 81. So I can't do the outside logarithm before we know what's the input of that, which is another logarithm. So you have to start first here. What's log in base 3 of 81 equal to first? We say 3 to the x, so 3 to what exponent equals 81? I have to rewrite 81 as a power in base 3. So 81, what 2 numbers multiply get you 81? 9. Now take each 9. What 2 numbers multiply by get you 9? 3 and 3. How about the other 9? 3 and 3. This is called factor tree. You remember them? Okay. Then means 3 to the x equals 3 to what exponent? 1, 2, 3, 4. 3 times 3 times 3 times 3 will give you 81. So 3 to the 4. So that means our logarithm base 3 of 81 equals 4, right? X is 4. Now you can go back to the original question, log in base 2 of log of base 3 of 81, which is just log in base 2 of whatever answer we got for this one, which was 4. And this one you can do without the extra work. You can ask yourself, 2 to what exponent equals 4? 2. That's right. If you don't see that, you can go again to the same process. Equal it to x, and then go 2 to the x equals 4, and then you'll see that it equals to 2. Right? So 2 to what exponent? 2 to what exponent equals to 4? That's the question you ask. This 2. The base, right? The base to what exponent equals to the number 4? And the answer for that would be 2. So a little bit of background information on logarithms. Okay, I won't ask you these kind of questions in a test, okay? But I wanted you to have a little bit more rooting into what the log is. But I think they're fun questions. Now we're getting into what we want to make sure we know for our tests. Getting into the parent logarithmic functions. So a parent logarithmic function has the general equation written as, oh, I missed my y there, y equals log in base b of x, with the following conditions, the same conditions we use for the logarithm of a number to exist. So the base has to be positive and different than 1, and the x, the number under the logarithm, have to always be positive, so bigger than 0. Okay, some examples. Y equals log in base 3 of x, or f of x equals log in base 2 of x, etc. So you notice that if we're just talking about a very basic parent function, all the changes from one to another is the base, right? So you have a variety of bases. How many parent logarithmic functions do you think they exist? Three numbers bigger than 0 and different than 1 are there? How many? Infinity, that's right. So there's an infinity of parent logarithmic functions that you can think of, right? Now, for us in this class, we're only going to be looking at two types of logarithmic functions that we do extensive work with. We do a little bit of other ones too, but once we get to modeling, we only going to look at the second type, right? But this is what I'm reminding you again, the notation. So log in base 10 of x, that's notation just for log of x, okay? So just because you don't see the base doesn't mean it's not there, okay? It's just notation because it's so common and extensively used. You just get tired of just keep writing base 10, base 10, base 10. So how about we get rid of it? But we all know that it's there, okay? Same thing for base E, Euler's number. We replace it by ln of x. Natural logarithm, that's where the n comes from. And I think it's French. It's like logarithme naturel or something like that. That's why it's in that order. Okay. So in the modeling part of our notes, we're only going to see the natural logarithm. Your calculators are only programmed to model using that, but they're so similar to one another. The difference between one and another is not substantial. So that's why you can use like the natural log for all of them. So if the trend of the function looks like a logarithmic trend, then you can use pretty much the natural log for most of them. Okay, so let's do some relating of equations and their graphs. First, let's introduce the logarithm of x, so just a logarithmic function. So for the graph of log of x, which is logarithm in base 10 of x, I'm showing you -10 there. So if I input -10, I want you to write that in your calculator. So write log, okay, and then input -10 in there. So you'll see how the condition for that log to exist appears as an error in your calculator. It won't let you calculate it because you cannot input in the calculator any number that's 0 or less, okay? So does not exist, okay, on the real answer. So does not exist usually what we write, okay? So all of the other negatives before and after, you can't really calculate a log for them, okay? How about log of 0? Same thing, right? Same thing, does not exist. So you can't really have any values for the x's right here. On the left-hand side, like there's nothing you're gonna get for a point for your function because I can't input any of these x's here. So I won't get a y value to correspond. Does that make sense? So that you can look at the graph, like that means the domain of this function will always be just x bigger than 0, right? Because I won't have a graph on the left-hand side of x0. Does that make sense? Okay. So that means, yeah, I can put in here, I can put 1, let's put actually 1 because 1 is a good number to calculate. So log in base 10 of 1 is what? Zero. So I get my first number. So you can put here 1. That's your first point there. And we're not going to draw this one to scale because logarithms are really hard to draw to scale. The next one is going to be at 10. I'm going to say that's where 10 is. What's log in base 10 of 10? Question mark 10 to what exponent equals 10? 1, right? So even without the calculator, you can answer that question. Same thing with the 1, too. Logarithm in base 10 to what exponent equals 1? The only possible is 0, because 0 as an exponent to a number always will give you the answer 1, right? So these two usually are the only ones that we sketch if we were to sketch a logarithmic function, because really the other ones are gonna get like quite fast out of the drawing or the margins we set up for our drawings. So what we have, once we have a few points here, we notice that as our x's get really, really close to 0, so from here, really close to 0 on this end, the y values are going to be negative, but more and more towards negative infinity, right? And as your x values get really, really large, the y values get also really, really large, okay? So this is the idea on the left-hand side of a vertical asymptote. Your graph will not cross that vertical asymptote ever, okay? It will just get really, really close to zero, but not at zero. Okay. And on the pattern, you can see how the pattern is kind of split up into two sections. On the first section from 0 to 1, your graph is really steep. That means the rate of change from one value to the next is really fast, right? I'm skipping up higher and higher and higher really fast. And then after I cross the x-axis, after you cross over your x-intercept, the increase is way slower, right? So when you have first a steep increase and then kind of slows down, that's what we call a logarithmic pattern, okay? And it can be this way, an increasing graph from quadrant 4 to quadrant 1, but you can also have the other way around when you have that vertical reflection, right? When you have a steep decrease at the beginning and then it kind of slows down in the decrease, okay? So the domain of the parent logarithmic function is x bigger than 0. The range is all of the real numbers. All of the real numbers, right? It covers all of the y's. The graph of a parent logarithmic function will never cross the y-axis. Remember, the exponential function never crosses the x-axis, right? And that means because we don't cross the y-axis, we won't have a y-intercept for these functions. The imaginary line, this vertical line right on top of the y-axis, so through x equals 0, that's called vertical asymptote. Usually after this page, we're just going to write it as VA, vertical asymptote. And then the x-intercept is always going to be at 1. Now let's describe the trend like we've done a little earlier. The graph is going to be an increasing graph, quadrant 4 to quadrant 1. One more thing and then we'll move on. Now, most of the y values for the majority, the vast majority of the y values for your logarithmic functions are going to be like decimal values. The only nice values will be at any powers of your base, okay? So base 10 gave you the value of 1, okay? It's 10. Logarithm base 10 of 10 was 1, okay? Then everything between 10 and 100, which is the next power in base 10, 10 to, this is 10 to the exponent of 2, will be something decimal, 1 point something, okay? And then finally, when you get to log in base 10 of 100, you're going to get the value of 2, right? So anything between 10 that you input and 100 is 1 point something all the way until you get to 2. Okay, so they increase really, really slow from 1 to the next y value, right? The next one would be from 100 to 1,000. Everything is just 2 point something, okay? It doesn't get to 3 because only at 1,000, which is 10 to the power of 3, that log is going to give you value of 3, okay? That's what we're saying here. It's a really slow increase here, right? Very, very slow. Make sense? I hope so. Okay, so then we're moving on to some transformations of this particular graph. Oh, actually, no, I'm just going to show you how ln looks and then transformations, okay? The same thing like before, because it's the same rule for all logarithms. You won't be able to input anything that's a negative or 0, okay, in any logarithm. Doesn't matter what it is. And then if you put 1, Try it in your calculator. What happens when you do ln of 1? ln using this button, which is the base E logarithm. What are you getting? 0. It will always be the same. It doesn't matter what logarithm you calculate. Okay, a logarithm in any base of 1 will equal 0. Okay, and then what happens when you enter E now, which is the same as your base? What you're really entering in your calculator is ln of E, right? But the base is already E because we have the notation for it. Your E button is above the division sign. It's right there, so you have to use the second to get to it. 1, that's right. So when you have the same base, when you have the same input as your base, your answer will always equal to 1. The same thing we had on the previous page, we had log in base 10 of 10, that equals to 1, okay? And then same like the previous one, anything in between E now and the next one that will give you number 2, which is E squared, the next power, right, of that base, will be just decimals, okay, and so forth. We're only going to need to graph these 2 points. So 1, 0, and then we need E, which is approximately, remember E is approximately 2.7. So we need 1, 2, 3, so 2.7 would be at 1. So you cross at 1, and then you go to the next point, and it always looks like this. And you have a vertical asymptote. That's either or 2.7. Absolutely, every single one of these characteristics will be the same as the previous function, okay? So x must be bigger than 0 for the domain. Y is all of the real numbers for the range. We will never cross the y-axis. That means we're not going to have any y-intercepts. We will have a vertical asymptote at x equals 0, and the x-intercept will be at 1 for this one too. And we got an increasing graph, quadrant 4, quadrant 1. If that was too fast for you, just write same like the previous page. Okay. Now we're getting to transformations. We don't have many for this one, actually just the reflection and lattice and compression. So for the logarithmic functions, we're only going to look at how they change if you put that number a there in front of it. And if that number a is negative, we will see a vertical reflection, just like we have seen for exponential functions. And if that number a in absolute value, that means I'm ignoring the negative, just the digit itself is different than 1, you'll either have a stretch or a compression of that graph, okay? So we will see stretch or compression. So let's start with the vertical reflection. We're going to use the parent ln of x, and we're going to look how it changes if we have that negative in front, okay? That's all we're doing. A is negative, and in this case, particularly just -1, okay? So we start with the parent function, crosses at 1, and then E1, that's 1. So that's the parent, which is ln of x. You can see the parent right there, ln of x. So -1 sits in front of ln of x. And they do have a vertical asymptote there. So all that negative does, it flips this graph in the vertical direction, right? Now you have to be careful with it because you have two parts. So this top part flips downward and you have a point there. So you have this arm like that. You see the reflection, right? It's the same graph, but in a different quadrant now. And then this other arm here goes in quadrant 1. So they just switch the quadrants. So overall, if you look at the graph now, you have a decreasing graph from quadrant 1 to quadrant 4, right? Because of that vertical reflection. So that's the graph of negative ln of x. Now, where is this point in particular? It's going to be at the negative value of whatever y that was. This y is at 1, okay? Here it's going to be at -1, right? So this point itself is e -1. And the point x-intercept won't change, okay? Because that's just with y 0. And that's 0 times -1. It's still going to be at 0. Now, again, all except for, actually, yeah, except for the end behavior will be the same thing again. So x bigger than 0, y is all of the real number, never crosses the y-axis, so no y-intercept. We have a VA still at x equals 0, and x-intercept stayed at 1. Even though we put a negative in front of it, it's still at 1. But then the end behavior is different in the sense that now it's a decreasing graph, okay? So decreasing quadrant 1 to quadrant 4. Now we're going to look at when the absolute value of a, that number we're going to multiply our log by, is going to be changing from 1. So if a is going to be bigger than 1 in absolute value, then you have a stretch. So it's stretching vertically. And then if a is going to be a number between 0 and 1, then you're going to have a compression vertically. It's compressing. We're going to use the parent function log of x to visualize both of these ideas. So let's put 1 there. Let's put 10 there. Again, this is not to scale, just to be able to visualize it. And let's put 1 on the y-axis there. So I have x-intercept there, and the next point at 10, 1 for the log of base 10 of x. So that's the log of x. And let's do the same thing for the other one because we're going to use the same base function. We're going to have them set up. Okay, so now this a is bigger than 1. That means that we have to stretch it vertical by the factor of 3. That's how it changes. So if you had this point at 1, now it's going to be at 1, 2, 3. So it'll be right there. This one is at 0 with the y. It stays there. So you basically have that visual of a stretched graph. Like After the x-intercept, you'll be above the graph. Before the x-intercept, you'll be underneath the previous graph. That just means it's steeper here and it's steeper there. We call this one, just like with exponential one, a faster increase, okay? Just like we're gonna call this one a slower increase than the previous graph. For the 1/3, this number is, the 1/3 is between 0 and 1, this a in absolute value. That means we're going to have to change all of the y's of these functions by multiplying them with 1/3. So this point that was at 1, it's going to be at 1/3 of that, somewhere there. It's going to be so hard to sketch this one, but that's the look of it. So we're going to call this one a slower increase. So after that one, you'll be underneath the graph. Before the one, you'll be above the graph, because this one is slower increasing here, and here it's going to be slowly increasing there, right? Then the one from before. They both have vertical asymptotes. They don't get affected. You're not going to have anything here. It's the same. And then all of these characteristics are the same as your parent function characteristics, okay? With the only difference that it's faster or slower, depending on that a value, okay? So x bigger than 0, y is real numbers, never y-intercept doesn't exist. We have a VA at x equal to 0. X-intercept still at 1, hasn't changed. And that means we have a increasing graph, quadrant 4 to 1, either faster for a equals 3 or slower for a equals 1/3. Okay. Now let's make a summary of everything so we have them nicely done. So pick system of axes. For a that is positive, a being this number in front, you would have an increasing quadrant 4 to quadrant 1. That is a equals 1, basically, right? And a positive, or a in absolute value equals 1. If a in absolute value is still 1, but now it's negative, so basically -1, you will have the vertical reflection of that graph. So like this. That means a in absolute value is still 1 for those. Now let's add in the stretch. So a in absolute value is bigger than 1. Remember the example from the previous page, it was 3, right? That means you would have to have a faster increase. If you also have a reflection, you would have a faster decrease. Okay, for the same a in absolute value being bigger than 1. So you would have increasing quadrant 4 to 1. And I'm going to put in red faster because only if your a in absolute value is bigger than 1. Okay, it's faster than the previous one. And for the other one, we have a decreasing quadrant 4, 2, 1. Again, faster. In the case of absolute value of A being bigger than 1. The other two are, again, the same graphs, because for these two columns, we have the same graphs, A bigger than 0, A less than 0. So the regular value for your values for your function, and these ones are just the vertical reflection. So you would have increasing quadrant 4 to 1. So that's A equal to 1, just to give us a reference when we do the slower part. These are all crossing at 1, right? All the time. So now we're looking at an A that's in between 0 and 1, like the previous example was 1/3, right? That means we're going to have a slower increase, like that. And if you have also the negative, you're going to have a slower decrease. Increasing 4 to 1 slower, decreasing 4, decreasing for both of these 1 to 4. The direction is always the direction of drawing. So from 1 to 4, we decrease. From 1 to 4, we decrease. And now x-intercept is always going to be at 1. So 1, 0 as a point. Y-intercept, we don't have, none, does not exist. The way to figure out the slower, faster is you just look to see how close they are, like these arms to the x-axis. They're really close to the x-axis, really very likely you're seeing a compression there, right? If they're just steeper further away from the x-axis, then it's very likely you have a stretch of the parent graph, okay? So let's do some examples of everything that we've seen so far. The first example is just an application of the logarithms that we've studied so far. And this kind of question I will be asking you in a test, okay? So if you want to know what kind of basic knowledge logarithm questions she'll ask, I'll ask you something like this, okay? So consider the logarithmic function y equals -1/2 of ln of x. So one question I would ask you, what kind of basis logarithm must have? It's just notation question. What is the base that's hidden in this notation? There's only two options that I gave you. E, that's right. So everybody should recognize the two bases that we've seen for notation. The ln is with base E, the log is base 10, okay? Now, I will ask you to calculate the value when you know an x, okay? And you're not going to use the application part of your calculator, that graph. So just a straight calculation, the way we calculated when we did the table of values for our functions. So ln, so you got to put ln here, because you're working with ln, but you also have a negative 1/2 in front of it. So negative 1 divided by 2, or 0.5. And then you put ln, and you plug in the x, which is 20, like that. Enter. So negative 1.497. So approximately nearest 10, negative 1.5. So negative, and I put bracket, 1 divided by 2, and then I pressed ln and plugged in 20. Okay, and I got that. Okay, huh? Did you try your calculator? Yeah. Make sure you put this negative, right? This one, not subtract. Yeah. Okay. Okay, now the next questions are some thinking questions, but they will be exactly the same in everything that I'm going to ask you in the future. So the question is, for what value of x, okay, the expression, this function, will be equal to negative 1/2. Now, in order for that, for negative 1/2 times ln of whatever this x is to equal to negative 1/2, that's what the question is asking you. This logarithm of that number x must be equal to what number? What number times negative 1/2 equals negative 1/2? 1, right? So basically what the question is asking you is ln of what number equals to 1? Now think back of the two examples we've done. Logarithm in base 10 functions and logarithm in base E function. At what value of x, we always got the answer 1. You can flip back to those two first functions we wrote down today. What x gave us value of 1 for the log and base 10 function? For ln was E, and for log was 0. Not 0. Like 10, that's right. So how is that related to the logarithm itself? So logarithm in base 10 of 10 equals 1. And then you said logarithm in base E of E is 1. So you can only get 1 if the input number is the same as what? As the base of the logarithm, okay? That means if this is ln, what do I have to input here to get 1? Same as the base, which is, what's the base of this logarithm? We already said it, E. So it has to be E. Okay, so it always has to be same as the base. Now let's test it out. Let's check it. Check. If I do negative 1/2 ln of E, do I get what the question tells me I should get? Negative 1/2. Let's check it. Negative 1/2 ln of E. Got it? Okay, good. So it's always going to be E. The next question, also a thinking question. For what value of x will the value of this function equal to 0? So the question is, negative 1/2 ln of x must be 0. Right? For what x will equal to 0? The only way 1/2 times something, the something being the logarithm, will be 0 if the ln of x is 0 itself, right? 0 times a number is always going to be 0, right? So really what the question is asking you is this: ln of what number is 0? Back to our two functions, what x do I need to make it equal to 0 for my logarithm for both of those functions? What did we input? Look at the table of values. X was what when we got 0? Both were 1, right? So the only option here, and for any other logarithm, will always be 1. The answer to this function, okay? 1. You can check it. Negative 1/2 ln of 1 equals 0. Plug it in, you'll see it will equal 0. Lastly, describe how the function y equals negative 1/2 ln of x comes from the basic or parent function ln of x, and then sketch the graph of negative 1/2 of ln of x. Well, you can just rewrite it like this, and then take it by parts. The negative, it's just a vertical reflection of your parent function, right? That's what we discussed. If I have a negative a, I will have a vertical reflection, right? And then only the number, the digit, the absolute value of that will tell me if I have a stretch or a compression. What do you think I will have? A stretch or a compression of the original function? A compression, right? Because 1/2 is in between 0 and 1, we will see a vertical compression of ln of x. And because a here is less than 0, we see vertical reflection of ln of x again. Sketching the graph, you can do it in parts. You can do this first and then second, or just do it all at once, okay? So the original graph is 1 and an E and then 1 there. That's your ln of x graph, your parent graph. Your parent function. And the first thing that changes it is vertical reflection. So you're just reflecting it vertically. The second thing that changes the graph is that compression. So then now you're going to compress it by a factor of 1/2, but we're not going to be too accurate with this. And that red graph, that's our final graph. So basically, when you're done all of the steps of the transformation of your function, that gives you the graph of -1/2 ln of x, because it includes all of the steps in it. Right? So the reflection happened and then the compression happened. That's your last step. So that's the graph of -1/2 ln of x. What's the green graph? If I were to give it an equation, what's going to be the equation of the green graph? That's right. That's the only thing we've done in step 1, right? Just the negative part of that. And then the 1/2 is going to be of this negative ln of x, right? That's the one we compressed. We didn't go back to the original one, right? Maybe we'll put that in of the negative ln of x. Example 5. Predict the x-intercepts, the y-intercept, and behavior, the domain, and the range of the function y equals -12 ln of x. So we have a logarithmic function where a is negative and the absolute value of a is bigger than 1. I always like to start with my end behavior. I don't know why. Just gonna, that's the more complex one, but end behavior for this, you would have a, this is your normal parent function. And then because your a is bigger than 1, you would have it much faster decreasing, okay, like that. Then you quickly can describe this end behavior is decreasing quadrant 1, 2, 4 faster, right? Faster than the ln of x, faster than negative ln of x. Okay. Then because it's a logarithmic function, we know we have x-intercept at 1. No y-intercept. Domain is x bigger than 0. Range is all of the real numbers. So these are always going to stay the same for you, right? You don't have any variations from that. So because the log function, you immediately know it's going to cross at 1, no y-intercept. The domain is bigger than 0, x's, and then y, all of the real numbers. Any questions? Okay. Matching the graphs with the corresponding equation. So we're only going to look at the A and B, and I'm giving you C and D, I think, in your turn here. So match the function graph at A and B with its corresponding equation, provide reasoning. So we're focusing on the graphs, and we try to deduct what we're going to see in the equation. So for graph A, I'm seeing a increasing graph quadrant 4 to 1 with no y-intercept, right? Which means for me, Therefore, it's going to be a logarithmic function, right? That's how I know it's logarithmic. And the x-intercept is at 1. Now, I do think that it's going to be a stretch graph because I see the distance between the x-axis and that second arm of my function, right? So it's going to be a faster increase for a. Now, you only have two increases, the a and the c, right? This will be a faster one, and this will be a slower increase. So all you are looking for is an a value that's positive to get that trend, and the absolute value of a must be bigger than 1 to get that faster increase for a here, right? So that's what I'm looking for in my equations. Which one is it? I need a that's positive and bigger than 1. Here. Okay. For B, we see a decreasing quadrant 1 to 4. No y-intercept. You can even call here this one slow decrease. That means is a log function. What kind of a? For decrease, your a would be negative, right? Because you had that vertical reflection happening. And for slower means your a in absolute value is between 0 and 1. So you're looking for a negative number between 0 and -1, basically. 3, 4, 4. So that's your B, and that's 4. Now, there are more transformations that happen to a function that could happen to a function that we don't discuss. You could actually take a graph and shift it left, right, up, down, right? So that's possibilities are there. So just not to say that this is it for logarithmic functions or for any other kind of functions that we looked at transformations. These are the only ones that we discussed at this in this course. Okay. Okay, so then break time 3:14, so let's go to 3:30, and then we're going to do modeling after that. 3:30. And you see, the modeling does have a little bit of extra. We'll talk about that extra one. Okay. Modeling with logarithmic functions. For us, the only modeling equation that we will get from a calculator would be this formatting. It would be your basic function times the number in front of it, okay? In this case, it's just called B, but it's, again, doesn't really matter which letter it is, okay? But you also have plus A there, so you have an extra value, okay, for your function. So that's a little bit different than the previous ones that we've seen today, okay? But that's going to be generated by your calculator. So it's written here, not there, so it's not confusing that the A is added to the X there, but you basically could be looking at it like this too. Y equals B times ln of X, and then plus A. So the ln of X, you always have to think about it as its own chunk, okay? So you don't put extra things in it. So example 7, we're going to do this one. The euphotic zone is the upper 200-meter layer in an ocean. Very little sunlight penetrates deeper than 200 meters. So most plants live in this zone, the 200 meters zone. As a result, 70% of all photosynthesis on Earth occurs in the euphotic zone of the oceans. That's kind of mind-boggling to me. The table shows light penetration data for a location in the Pacific Ocean. So when you have 100% of sunlight, you have 0 meters. That means at the level of the water, right? And then you go deeper halfway, so 54.37, you get 20, at 20 meters, you get 54% of that sunlight penetrating to that level. And then as you see, as you are deeper and deeper into the ocean, this one is 100 meters, your light is smaller and smaller, right? So the question asks us to take this data and determine the equation of a logarithmic regression for it, okay? And then answer some questions. Determine the amount of sunlight that penetrates to a depth of 200. So what is this sunlight over here, right? So obviously we're looking for a really, really small number, right? Does that make sense? Because at 200, we already, like, we are in the darkness. So there's going to be no light almost there, right? So one way to determine if your data is logarithmic data or not, you look for the pattern, right? Now, this one is a bit backwards because your x's are decreasing. So you can look at it backwards. You say, as your x's, as they are increasing, what happens to your y's? They are decreasing, right? So that would be like this pattern. As you go to the right of your x, your y's are decreasing, right? So you have that. Then you can look at the steepness of the change too. So here they're changing a bit. Their x's are increasing a little bit slower here, but the y's are changing drastically. And then your x's are changing again, and then the y are changing faster and faster, okay? So that's a pattern of your logarithmic function in the decreasing fashion. So we already know how to enter data in our calculator. So second is the second one, just straight stat, and then calc, and put your data in. I already did that during our break. And then we want the logarithmic regression equations. So stat, calc, the logarithmic is, let's find it, not the linear, okay? You don't want to confuse it with the linear. It's at 9, ln regression. So we get the A 151.211, etc., and B negative 32.836, etc. So I have it written down in your notes, the way you would plug them into your calculator, right? But you can copy the same thing like you see in your calculator screen on the page. I'm not against that. Just make sure you include all your decimals. Okay, so now we have to answer. The question is, what is an x when you're given a y? The pattern we always use is in the y1, we put the equation, right? In y2, we put the y that's given, and we are solving for the intersection point, so we can reach that x of that intersection point. So let's graph first and see how it looks like. Oh, I'm graphing a previous equation. Wait, I have to erase it. Clear. So let's transfer with vars. Vars 5 EQ, enter. So first the equation and then 200, okay? And then graph. Now what I want is I want the intersection. So the 200, I definitely won't see very clearly. Because look at my window, the maximum is 200. So basically, exactly what the line is at 200 is the margin of the screen, right? So what I want to do is get closer to that 200 if I can. So maybe I'll go the minimum to be 180, and then this 220. Trial and error. There's no way you can get it all the time the first try, right? But I know around what values for y I should be, right? But same for the x's, right? Because I know it's gonna have to be lower than 4.76. So I can set my x's to be between 0 and 5 if you want, just to see what happens. So between 0 and 5, it's gonna be my first try. And please notice how I'm using the data, right, to guide myself what kind of window I'm really needing to see what I'm trying to see, which is the portion of the graph that shows me where this intersection point will be. So I'm going to graph it and see what happens. Okay, so I see the intersection point right there, right? So I want to figure out what that is. Second trace, 5 for intersection. And then let's see where my graph is. I think I'm going oppositely. If you watch your Y, you'll know if you go higher or lower. If your Y now gets smaller, that means you go in the right direction. Am I going the right? No, I need 200. Never mind. I have to go to the Y equals 200. So I'm down here right now. So I have to get to the 200 there. So I do want them to get higher. Y is 200. It should show up. There it shows up. So you're around the intersection and press enter 3 times. So a light penetration of 0.22%, so less than 1%, okay? So darkness at 200 meters. What's the lowest, what's the deepest that you can go in the ocean? I think it's Mariana's Trench is the deepest, right, is it? Am I saying something stupid? I know it's really low. Lowest ocean depth is what? Let's ask Google. Because it's definitely not 200 meters. I just want to like kind of put your perspective for you, the darkness that is happening in the ocean. The lowest or deepest depth, I don't know if that's good English, deepest point in the ocean. Oh, it's cold. Yeah, it is Mariana's Trench. Oh my God. Okay, Challenger's Deep is cold at 10,984 meters. How much light do you have there? Nothing. Okay, so then we read the X for that one, and we say 0.23 approximately of sunlight at a depth of 200 meters. So all of these questions, again, are very, very similar, right? You just have to get the pattern. Are you looking for an X? Then you do Y1, Y2. Are you looking for a Y? You do just X, so a second trace value. Okay, some questions, not the ones that I give you for tests, but some questions might be tricky in the way they are set up. And you have to be able to identify which is the input and which is the output of the function. So let's read example 8. It's telling you that time is a function of population, can be approximated by a logarithmic function. The table below shows the population of Alberta in 10 years interval. Okay. So time as a function of population. So this wording, function of population. if you write that down like this, function of population, you immediately know with this notation of your function, what's going to be the input. The input or the X input is the population. What's going to be the output if the input is the population? If you look at your table, what's going to be the Y or the output? Yeah, the time, the years, right? And the reason why I'm doing this question for you is because the way they give you the table is backwards, right? The first column of the table is time, and the second one is population. And if this would be a question for you to figure out how you put your data in the table, you would have to know that I have to put the population in the L1, and I have to put the years in L2. Okay, this is a continuation of the table. So just imagine taking this and putting at the bottom here, right? I don't do that to my students. I don't trick them into thinking which one is X and Y. But the reason why this is allowed is because you can use the same data to actually describe this example with an exponential function, right? But it would be different, right? It would be the population is a function of the time for the exponential function. They're just backwards, okay? So the X and the Y input outputs in the exponential function, they just are going to be vice versa, okay? That's why it's allowing for this. So create a scatter plot to show how time is related to population. So that just means just a scatter plot. All of the other thing is extra. All you need is a scatter plot. So you just have to put the data into your calculator. So on stat edit. Let's clear that. Let's clear that. Now, the reason why when you put the big number here, you're not going to see the whole thing, is it doesn't have any space, but it will record it as a whole number in the line when you enter it. Just in the table, you won't see it. So you start with 2,974,807. So you see that 2,974 over here, but then when you press enter, you're only going to see the scientific notation of that number. So there's no room, okay? And then you keep going to, I'm going to make an error for this one, too many numbers. 545, 553, and then keep going. Okay, it's the moment of truth now. All my numbers. Okay, so let's see. The scatter plot should be straightforward. The plot is on Zoom. That there it is. Determine the equation of the logarithmic regression function that models the data, and then let's describe some of these characteristics for this data. So first, the equation. Oops. Mhm, 9, right? Yeah, oh, I got it. So for A, y equals a plus b ln of x, with a is negative 346.0896827, and b is 28.95741,502. Okay, let's put that equation there and see what happens. Statistics equation into the y equal. And we want to know where that intersect is, right? So what x will give us a zero population? Now, x is population, the other way around. What population will give us the year, the beginning, 1900, right? At 1900, that's your zero here, because these are the years after or since 1900. So at the 1900 year, which is for us zero, what's going to be the population, right? So second trace, we want zero, right? We are asked for x-intercept, yes. The y-intercept we don't have. So left bound, I'm going to give myself a bit more window. I don't like that. X, y minimum, negative 50. Second trace. Second trace, zero. Left bound would be with the negative zero, negative y value. So you want to watch for that y becoming negative. And then right bound would be positive. So just enter. So a population of 155,077.06. That's what the model is telling you. When you look at the value here, it doesn't really make sense, but it's because you can see your model doesn't hit every single right value. It's just a model for this kind of trend, right? But that's what it is. The x-intercept of your model would be at 155,077 approximately. And that's, remember, that's for the year 1900. Even though for us the y is zero, that zero represents the year 1900. And behavior for our graph, it's an increasing graph, right? Quadrant 4 to 1. And that takes care of the whether the function is increasing or decreasing question as well. It's an increasing. The domain and a range, the domain x is bigger than zero. Population makes sense that too, right? Population always must be bigger than zero, right? people more than 0. Okay. And the range, all of the real numbers for the range, but if we're looking at the particularities of our function, right? If we only look at the years since 1900 for the range, it will be just bigger than 1900 and 1, right? So 1 and above. But we can also say 0, bigger than 0. So 0 years from 1900 and above from that. For the actual model though, like the range would be all of the real numbers, right? Because the model itself doesn't think of, oh, this is population, oh, this is years. I have to take care of what kind of numbers these are, right? But if you think about the application of that question, does it make sense to have that? Then you can just think about only the application for the description of your range. And part C, this time you have to use the equation. So interpolate the year in which a population exceeded 2 million. So the years are Y. That's the question. What is the year? And you're given the X, 2 million. So this pattern is just second trace calc, right? Value. I'm gonna put 2 million. And we're gonna get an error if, Hannah? Are we gonna get an error with the 2 million here? Not an error, but if we were to get an error, why? Yes, because it doesn't include 2 million, it just happens it does, right? But yes, if you don't have in the window the X max or like to include that value or the min, whatever the number you're inputting is, right? Then you have to make sure you adjust that to fix it. So second trace value, 2 million. 74.04. So the year is going to be what? Because it's years, the X is the, no, the X, the Y is the years since 1900. So this would be 1974.04. So we want to exceed the 2 million. So we're going to say approximately 1975. Because we want to exceed 2 million.